Hello everyone, welcome back to another lecture on regeneration biology. And in today's lecture, we will learn about tissue engineering, why and how. By now, we have learned about how regeneration takes place and how regeneration allows certain organism to survive effectively than the rest. Now we are stepping into the next stage of making organs for human benefit. So the introduction of tissue engineering is important because we need to know where does it sit or where is its strategic position. So tissue engineering is an emerging interdisciplinary field that applies the principles of biology and engineering for the development of viable substitutes that restore, maintain, or improve the function of human tissues. There are plenty definitions, one of them being this. And it's a Venn diagram where this is biology principles, this has engineering principle, and this has medicine principle. And all three overlap in a triple point. That is where tissue engineering lies. In other words, we can say tissue engineering require all these three subject area: biology, engineering, and medicine. Tissue engineering is a field that combines biology and engineering and is rapidly evolving these days, offering the potential for regenerative medicine and organ replacement. Current advancements include 3D bioprinting, stem cell therapies, and advanced biomaterials with future scope focusing on personalized medicine and organ regeneration. So this is the place where it is going to, like you stitch a dress for your fitting, or you make a shoes or something which is fitting your legs, or you make an ornament that fits you. Same logic is getting into tissue engineering as well. Tissue engineering uses a combination of cell engineering, materials and methods, and suitable biochemical, physicochemical factors to improve or replace biological tissues. So, we should also understand when you use the word tissue engineering, it need not necessarily make a full-fledged organ. It can also happen, say you are replacing a heart valve. Actually, it is a flap. So it need not necessarily be a full-fledged organ, but it is part of an organ. Or in other words, you are fusing the middle of a broken bone. If a bone is supposed to be 1 feet long, a 10 centimeter piece is lost. Now you have an option of putting a metal rod versus you have an option of putting that 10 centimeter portion artificially, which is a biological material, into the middle. And now the 1 feet of the bone is restored. So you should keep an idea in your mind that it uses different strategy based on what tissue or what organ you are trying to fix it. It need not be a full-fledged organ. Tissue engineering involves using tissue scaffold to form new viable tissue for a medical purpose. We will see more in detail about scaffold, but time being, you understand scaffold is a matrix, extracellular matrix. All of you know by now because we discussed about it a lot. It is something similar to that of ECM, or you can think about the pillars and beams of a building. You make a building not always on the walls. Many buildings these days you make, say, 30 floored building, 50 floored building. You don't make those buildings on the walls. You make the skeleton of it and then fill the gaps with the walls. Same logic, the beams and the pillars are the scaffold, and the walls and the bricks are the cells. So this is the idea you should have. So using the right scaffold holds a lot of potential during a artificial tissue or an organ production. While it was once categorized as a subfield of biomaterials, the scaffold, having grown in scope and importance, it can be considered a field on its own as of now, because Lot of journals are there which has the name of biomaterials, or some of them are exclusively dealing with the scaffolding or scaffolding properties of various biomaterials or artificially produced chemical or physical materials also. For example, using fibroblast in skin replacement or repair simple tissue. Say you have got a huge tumor on the face, doctor removed it, and you don't have a cheek at all. Your whole mouth, interior, everything is seen. But they're filling the gap with the naturally looking your own skin. It makes a hell and heaven difference. So one may think, oh, skin is not a major organ. How does that matter? It depends on which part of the body you are discussing. Some part it will become extremely important. Same way, say tip of your nose. It won't look proper at all if your nose is broken and you don't have a proper nose. So that time, that simple flap of tissue makes huge difference in the appearance of the person. Cartilage is repaired with living chondrocytes. These are all simple tissues, no complexity at all. If you can make from the same person and you put it, that makes lot of difference in the life of that person, affected person. We will see more examples. Regenerating a human ear using a scaffold, which is extensively done due to some accident or something. You lost this external hood or the pinna is lost, so it will look very odd, so you can replace it. Although it's a simple structure, of course it helps in listening properly without echo, etc. These foldings, flappings, everything has got a biological role. It's not that you have your ear formed with, it's not smooth, it's not looking like an umbrella. You should not think like that, because this plays a major role in your listening ability. And also in vitro meat, you can make meat when you don't have enough animals to sacrifice, or someone is thinking killing animals is bad but you still want to eat meat. So then in vitro meat is possible with this tissue engineering. Bioartificial liver device, artificial pancreas, artificial bladders. Urinary bladder means cartilage, which is lab grown tissues, was successfully used to repair knee cartilage. Knee is a very sensitive organ, and knee cartilage is very important to get replaced upon injury or a damage. Artificial skin is constructed from human skills embedded in a hydrogel, such as the case of bioprinted constructs for battlefield burn repairs. Many soldiers who get injured very severely in battlefield, repairing them require a lot of such artificial skin. Artificial skin means not that some artificial material, it is skin only which is made artificially. Artificial bone marrow, artificial bone, oral mucosa, tissue engineering, and foreskin. So these are all some part of the body which needed in a different scenario. So this is a picture of artificial ear, artificial trachea, and artificial bladder formation, urinary bladder, and tissue engineered heart valve, and lab grown mice kidney. Many examples are there. These are some of the pictures to know. These are all meant for transplantation into human body, different parts. If you look the different steps of tissue engineering, step 1, get the tissue sample from the body, usually done via biopsy. We will see about these steps much in detail. Now we are seeing the outline and the principle. Step 2, after you collected the cell from the person or the patient, grow the cells into new tissues. Cell isolation, cultivation, and scaffold and seeding is involved in that. So you have to grow these biopsy cells and pick up that a given type of cell what you would be proceeding further, and see whether this cell can happily grow. Are they healthy enough? Then you identify a scaffold where you want to populate them, and then colonize them, provide them the medium so that the cells will grow over the scaffold. Normal cells cannot climb over each other because they are very, they follow the rules. Only cancerous cells can climb on each other. Normal cells, if they want to grow, then they should have a scaffold, then only they grow. Two cells cannot climb on each other because they have something called contact inhibition. And then comes the implanting new tissue, that is implantation and detection. Implantation means delivery into the recipient or the patient, and then detection of its normal function and its stability. So the basic process of tissue engineering can be in a nutshell. You can put it here. You harvest the cell and proliferate it, and you also choose the correct scaffold and then seed the cells onto the scaffold. That's called cell seeding. And then you put this scaffold with the cells, seeded cells, into a bioreactor in which the culture medium will be pumped and cells will proliferate, and this newly growing cells will produce their own ECM, extracellular matrix, and eventually the scaffold will disappear. These scaffolds are no more necessary. So that is why the selection of the scaffold becomes so important, that you don't want that scaffold to hang around. Just like absorbable suture, you may have heard about in some surgery. If you have an external wound and an internal wound, internal suturing doctors will do using absorbable sutures, so that those sutures will get absorbed into the body. You don't have to remove the suture. External one, after a few days, 10 days or something, doctors will say, okay, you come, I will remove those sutures so that your injury is healed. So something like that, these matrix should disappear. That is, the scaffold should disappear and it is replaced by the matrix. Then only you can claim, oh, it is a normal cell. And the outlet of the used medium will go as waste and it will be expelled, and you end up getting a engineered construct. Construct, what does mean is constructed tissue material, and it can be nasal, septal, quadrilateral cartilage, this one. So these are all vulnerable for damage in road accident or battlefield, etc., and they can be replaced. Let us see what are the clinical applications. Bone and cartilage regeneration. Tissue engineering techniques are being used to repair bone and cartilage defects. Skin grafting. Engineered skin substitutes are used to treat burns and wounds. And oral and maxillofacial rehabilitation. Tissue engineering offers viable alternatives to traditional bone healing techniques, because bone healing or bone grafting techniques are very slow and less efficient. That is why tissue engineering gives you adequate opportunity to to make whatever shape you want to give. Like, if you are expecting the bone to heal in a natural way, it may not grow the way you want, because you cannot tweak the system in a living organism. But if you if you allow my nose to grow naturally, it may not get the proper shape. So already properly shaped one, you put it, it's a question of just fusing. So that is why making them proper shaped structures is very, very important. And gastrointestinal tract. Tissue engineering holds promise for treating GI defects, avoiding complications associated with current therapies. Current therapy, if you have to cut the colon off, then they have to run with a bag for to hold their stools, etc. But if you can put back an intestine with an artificially made intestine, then their life will become great. Heart tissue regeneration. Novel biomaterials and technologies are being explored to improve heart tissue repair after myocardial infarction. This we kind of discussed in the previous classes as well. The infarct, the fibroid tissue that is deposited will come in between. It's almost like, when you are happily eating some food, I am putting one stone in between your teeth. Then you can't. Your jaw will not come hit onto the food. So that stone should be removed. Something like that. This scar will come in between the contraction. That should be removed so that the heart efficiency is restored back. The challenges, there are plenty challenges, just like any other system has. It is the scalability and cost. In the previous class we discussed scalability, which basically mean, although the idea is perfect, you can do it, anything and everything you want, but it will give you only 1 microgram of tissue or 1 milligram of tissue. You want 10 grams. Then it becomes it's a hypothetical scenario. So tissue availability or scalability is very, very important. And the cost. While the scalability is a concern, cost cannot go proportional to that. It's like, you may have seen in the market, if you buy a 100-gram material, cost may be say 50 rupees. Same thing, if you buy 1 kilo, it may come for 400 rupee. Technically, it should have been 500 rupee. for 100 grams. So when you buy more, normally it will be cheap. But whenever you say other things, say you are buying 1 meter of dress, cloth. If you buy 10 meter, it will be, they will not give any discount. They will say 1 meter, they multiply with 10, they will say. So that logic may not work in the case of tissue, because sometimes when you need a large tissue, you should find a way in which that can be made cheaper, so that more and more people will get the benefit out of it. So scaling up tissue engineering technologies for clinical use can be challenging and costly. This is associated with that. So one should find what are the ways through which you can reduce the cost. Immunogenicity. Ensuring that the engineered tissues do not trigger an immune response in the recipient is very, very crucial. It will be almost like telling operation successful but patient is dead. So you made a beautiful tissue, everything is a transplantation, everything is done. Within 1 month, your body rejected it in spite of giving immunosuppressant. So one has to make sure that the so-called immunological targets are not overabundantly represented in these engineered tissues. So one has to take care of that. That's why we use the word humanized pig tissues or humanized some organs, we say. This is one angle is humanized, other angle is even between my tissue and your tissue will not be compatible, although you are also human, I am also human. So that's called HLA typing, that also has to match. So vascularization, creating functional vascular network with engineered tissue is a major hurdle. You made a tissue, nicely made a tissue, everything is fine, but how will you maintain? So far you have been maintaining the medium, you are providing culture medium and it was getting oxygen, nutrition, everything. But in your tissue, who will pour medium on top of these cells? Blood circulation should come. So when you make it, you have to make sure that the blood vasculature also is there in that tissue. Then, and it should interconnect with your existing circulatory system. Then only there is a future for that tissue. And regulatory hurdles. Obtaining regulatory approval for tissue engineering therapies can be complex and time consuming, because in the previous class we discussed about the ethics and morality of tissue culture research or the stem cell research. Same way, handling the regulatory hurdles is another challenge. So futuristic scope. What are the future? Personalized medicine. Tailoring tissue engineering therapies to individual patients' needs, their own cells and biomaterials can be used, and so that it will become like, oh, I have lost one finger, so I took my tissue from my body and made a new finger and fixed it. So this is what the idealistic scenario we are looking for as in future. Organ regeneration, developing technologies to regenerate entire organs, addressing the shortage of donor organs. And you don't need to worry about this vasculature also. I lost one finger and I am tweaking some cocktail here so that my finger is growing. I won't mind whether it takes 6 months or 1 year. As long as I get my finger back, I'm happy. So I don't need to culture it, and automatically my body is making blood vasculature into it. So these are all the future promises of regeneration or tissue engineering for regenerative medicine. Disease modeling, using engineered tissues and organoids to study diseases and test new therapies. This is another vista of exploration. And gene editing, utilizing CRISPR-Cas9 technology for gene editing to enhance tissue integration and function. Sometimes what happens, like a tissue I made it and that tissue has got some HLA type, and which if present, it is going to get rejected by the recipient. So what I can do is I can just knock down, mutate that gene. If it is not an important gene for the survival of the tissue, I can just get rid of that, which will be targeted by the recipient's immune system. So that host tissue, I can tweak it by CRISPR-Cas9 technology. I will not go into the details of CRISPR-Cas9 because it's a completely different field, but those who are interested can read about it and understand what do I mean. Advanced bioprinting, developing more sophisticated bioprinting techniques to create complex functional tissues and organs. So this is a bioprinting, where you make like a 3D printing. You can print the organ at will in a given shape and size and transplant. And integration of artificial intelligence. These days it's a time of AI everywhere. Using AI to analyze data and optimize tissue engineering processes, because while making a tissue, we should understand whether that particular tissue is going to give an additional burden on that patient. Say a liver was failed, now I am putting. So what is the pressure that organ is going to put on the blood pressure or any other internal bulk pressure onto that person, and will it withstand? Everything need to be monitored and calculated. That is why AI comes into picture. It won't go just by measuring the dimension. It has to be taken. It is a multi-parametric. That is why AI comes into picture. And microfluidics and this is based on the various physiological platforms, creating microfluidic devices to mimic physiological environments and study tissue function. That means you can use the microfluidic system to support these tissues so that they will get a benefit from the recipient organism. So tissue engineering, if you look further, you can see what are the scopes and their status as of now. The term tissue engineering was created to represent a new concept that focuses on regenerating new tissues. It is a spelling mistake, NEW, new tissues from cells that's with the support of biomaterials and growth factors. So we should understand that it is an integration of biomaterials and the live tissues. They come together, and that is, there is a new research field also that is called biomedical engineering, a new research in abroad, foreign countries. Many institutes give degrees and PhDs in that field also. India, it is still catching it up. This interdisciplinary engineering has attracted much attention as new therapeutic means that may overcome the drawbacks involved in the current artificial organs and organ transplantation that have also been aiming at replacing lost or severely damaged tissues or organs. So that is the essence of tissue engineering. However, the tissues regenerated by tissue engineering and widely applied to patients are minimal, including skin, bone, cartilage, capillary, and periodontal tissues. They are not gone into every organ. They have gone into some frequent, easily doable. They are restricted to these easily doable few minimal list of tissues. What are the reasons for such slow advances in clinical application for tissue engineering? Obviously, one can anticipate biological limitations and financial limitations. Both comes together. The fundamentals of tissue engineering involves cell sources, scaffolds for cell expansion and differentiation, and carriers for growth factors. But some tissue and organ differentiation we are still learning. We cannot just make it, okay, I have stem cell, you make liver, I have stem cell, make kidney. We haven't reached that stage of tweaking in every aspects of an organ formation. Animal and human trials are major part of these applications. Based on these results, some critical problems are to be addressed and resolved for the advances of tissue engineering are addressed from the engineering point of view these days, emphasizing the close collaboration between medical doctors and biomaterial scientists. So the current clinical status include patients are mainly treated surgically by grafting methods by three ways of approaches, that is autograft, allograft, and xenograft. What is an autograft? Autograft, to move tissue from one side to the other side of the body. Say I want some skin on my cheek. I took the skin from my thigh and cut open and I pasted here, switched here. That is one approach. Patient is already suffering from a disease, thus grafting the same body will be very painful, might lead to graft failure because they are not perfect. I got a trouble here not because I am healthy, I am having trouble, and making another wound in my body and trying to expect that wound to join can be problematic. So they are the drawbacks. In old age patients, the grafted cells and tissues might not regenerate or might not stick there after harvest because they are in their downward journey. Allograft means from another person of the same species. Person A donating to the person B. This method also have problems, suffers from issues like donor scarcity and immune rejection. Like I told you, HLA typing mismatch. You may have heard about it. Kidney donor, they give, father gives to son or mother gives to daughter, or that will be more authentic or more closer, or sibling donation is more closer than a stranger. Husband giving to wife, although people do it, but they don't have any genetical identity, so they have to be under severe immunosuppression. And also the donor should be disease free, otherwise what will happen? The donor had some disease, they donated the organ, and now the recipient also got that disease. So this is another problem. Disease means some infective viral infection, those kind of things. Xenograft include the tissue and organ taken from other species, say for example pig. Problems like biocompatibility and immune rejection are common in this method. Moreover, animal tissues are more prone to contamination than human tissues. So after grafting, the chances of infection still persist. So these are all some challenges which you should be aware of. Now let us understand what are the main angles in which tissue engineering is the only option. Why we need to go for tissue engineering. Some I already explained to you, like a bone of 1 feet, it became 10 centimeters lost. You cannot say, okay, now from today onwards, you can have 10 centimeter shorter bone, because the other part of the body will not integrate with that. So you need it. Then only you cannot have one leg longer, one leg shorter. They cannot. It is such an organism will not, and that will give extra stress on their pelvic girdle and backbone, and they will be bedridden soon. So although it is just a 10 centimeter shortage, you have to retain that original length for having equal balance of your gait and movement. So donor tissues and organs are always in short supply. Hence, the topic of tissue engineering itself comes into picture. To minimize immune system response by growing on cells or novel ways to protect the transplant. Like I told you, if I am tweaking the cells in a petri dish, I can understand it better and I can get rid of all the troublemakers. Oh, this protein is there, immune rejection will be there, let me get rid of that. Oh, this protein is there, it may give some trouble, it may cause some disease, let me get rid of that. So it gives you, just like you pluck some fruits from the wild and you clean it and take only the good part. Sometimes you remove the skin of a apple just to make sure that I don't want to eat skin, or I don't want some pesticides landed onto the skin. So multi-purpose, you clean, nobody eats the skin of the banana. You remove it and then you eat it. So it's not just about the taste, it also gives a protection. So ultimate aim of tissue engineering is repair, regenerate, replace, restore. So there are 4 R's. First is repair and or regenerate or replace and restore, depending upon the context. In some situation, you just need a repair. In some situation, it's not just repair, you need to regenerate that, otherwise then the scenario will not work. Sometimes you need to replace it, organ is gone, just like a kidney, they remove the whole kidney, they will not try to fix that broken or damaged kidney and put a new kidney. And then some situation it is restoration, that means organ everything is fine but some connection is affected, and you make the proper connection so that it will now start functioning. So there are different scenarios in which these troubles exist. So overview of tissue engineering process is been listed here in this picture. So this is a person, can be healthy or a patient, doesn't matter, and cells are collected by biopsy and a monolayer of cultured cells are made, and then you expanded these cells and it expanded them by culturing them, and then what it is been done is they culture a 3D polymeric scaffold, and this 3D polymeric scaffold is pushed into a generation graft, and this generation graft is now pushed back into the patient. So you can see here, this is the donor tissue, isolated cells, and you have made an in vitro culture and then you put into scaffold and in vitro implantation. So understand, these are the flow of regeneration process. We will learn more about regeneration biology in the next class. Thank you.